we will set outer void behind the water, the positive side of z-axis. So to check the geometry, so first we have to set eye control parameter equals 8. So first one is changing the eye control parameter from 0 to 8 to check the geometry. And second one, and the surface section, we have to add the surface at z equal 25 centimeter as number 14, like this. So second step is adding the surface ID number 14, and in this case the surface, so PZ, and the value is 25 centimeter. And third step, an outer void made of the cylinder has to be added by setting its material number equals -1, like this. So move on to the cell section, and please add the cell number 102, and please define the -1 to make a outer void region of a cylinder. So to make a cylinder, maybe -11, and outside the surface of 13 and inside the 14, surface 14. So I think this distribution is sufficient in this case. So and fourth, we need to modify the cell section so as to remove the double defined region. So we need to write sharp 100 like this. Doing the answer, comparing the answer to my modified input file. Okay, it's good shape. So let's execute the fix. Okay, the console says eye control equal X, so the correctly modified. So after the execution, please open the track underbar the exz.eps file. Oh, something wrong. I see. This value should be negative. Okay, I'll try the execution again. Yes, perfect. Okay, if you obtain this figure, the exercise number 1 is completed. Perfect. Okay, let's move on to the next exercise. Next, in this exercise number 2, we will record information on photons from the cobalt-60 source passing through the water as a dump data. Okay, we have to do is a 5.5 step described below. So first one, to do this, the first one, by copying the T cross study section, please make the second T cross section. The first one is used to make dump data, and second one is for using to check energy spectrum of the dump data. Okay. Next, second one, please add dump parameters from 1 to 9, 18, and 19 to the first T-cross study. And third, in the first T-cross study, please change the cell number so that this study counts the cross underbar photon dot out. And please set EPS out equals 0. Fourth, in the second T-cross study, please add one condition to count the number of photons moving from the cell ID number 101 to 102. So please set its area to be pi times 10 square in centimeter square. After these modification and these steps, fifth, please execute quits with I control equal 0 for transport simulation in the parameters section. Okay, from now, in the same manner as the previous exercise number 1, I will make some time. So please try this exercise using these hints. Maybe a little bit confusing and difficult, but please try this exercise number 2. When you finish this exercise, please let me know using the reaction yes. Let's try. Okay, it's time. So I think seeing the number of the people who completed this exercise, so I think this exercise difficult for everyone. So of course the answer is shown in the next page. So seeing the answer, so let's do this exercise together. Okay, moving on to the answer page. So here is an answer of exercise number 2. So seeing these steps, so a little bit difficult, even in case of the developer. So in this exercise, we will record information on photons from the cobalt-60 source passing through the water as a dump data. So seeing this answer, so let's do this exercise with me. So where is my folder? Oh, I found. Okay, so first step. So the easiest step is changing the eye control parameter into 0 in the parameter section. So first, changing the eye control parameter from 8 to 0, like this. And next, second one is copying the T cross tally, and making the second T cross section like this. So what we have to do is the copying and pasting like this. And third one is adding the dump parameter like this to the first T cross tally. Little bit complicated. So I have to add the dump parameters here. Dump equals -11, and in this line 1, 2, 3, 4, 5, 6, 7, 8, 9, and 18, 19. Okay, and fourth, in the first T cross tally, please change the cell number so that the tally counts the number of photons moving from cell ID number 101 to 102. I'm mentioning, I mean here. So as a third step, or not third step, as a fourth step, newly adding the cell number and like this. So from what to what? From 101 to 102. 101 to 102. Maybe it's better to copy and paste. Oh. Okay. Yes. Okay. Fifth, we need to set the file name of the first T cross tally to be cross underbar photon.out. So we have to change this name, cross underbar photon.out, and In addition, we have to change the EPS out parameter to be 0, and fix. In the second T-cross study, please add one condition. I mistake. I mistake. I modify this here as a which fourth step, and the fourth step we have to modify this. So not here. So change, better to change the 110 to be 101 and 102, like this. So I'm now changing like this. And then after that, as a sixth step in the second T-cross study, we have to add the one condition to count the number of photons moving from cell ID number 101 to 102, like this. So complicated. Maybe that's all. After this modification, let's execute the fits. Oh, something error. So 96 line. Oh, I forgot to change the leg number. So we have to change this leg number from 1 to 2 because the condition is 2. Number of the condition is 2. So we have to change this value like this. Okay, let's try again. Okay, completed. So after the execution, please open the cross underbar eng.eps file. This one. And going to the second page, then we can obtain the same result as the figure shown in this slide. Okay. From this figure, the data are not enough to be used as source because this result should be continuous spectrum. Okay. Before doing this exercise, let's take a mini break. I think the 5 minutes break. So after the 5 minutes later, let's resume this exercise number 3. So let's take a mini break, 5-minute mini break. Okay, let's start the let's resume the exercise number 3. And the previous example number 2. So we data are not enough to be used as a source. This is a very serious problem. So to solve this problem, so let's do the exercise number 3. This lecture is so simple. In this lecture exercise, we will make a large dump data can be used as a source. So all we have to do is very simple. All we have to do is one point described below. Please increase the max gas value to obtain large data. Okay, but it's very easy. What we have to do is just changing the max gas value to obtain large data. So from now, I'll make some time in the same manner as the previous exercise. So please try this exercise. When you finish this exercise, please let me know using reaction button, yes. So please enjoy. Okay, this exercise is so simple, maybe easy. So let's do this exercise with me. So the answer is also shown in the next page. So seeing the answer, so I will do the exercise number 3. So here is an answer of the exercise number 3. And what we have to do to increase the max gas value, what we have to do is to increase the max gas to, for example, 100,000. Of course, more value is better because the data become very smooth. But I will try using this value in this case. So really this example is simple. So only one step, just increasing this value, max gas value, 100,000. Okay. Then let's see what happened after the execution of the fix. Oh, really slow. Because the simulation number of the simulation particle is increased in this case. So the performance is slow, but completed. Okay, let's see what happened. So after the execution, please open the file cross_env.eps file and go to the second page. This one. And first page, and click this button and second page. As shown in this figure, the result becomes a continuum spectrum. This means the relative number are less than 20%. To check the relative error, so please open the cross_env.out file and go down to the second page and seeing these value, checking this value, and we can confirm the relative error, maximum relative error is about 20%. So this can be useful. This can be used as a source. Okay. Okay, next, let's learn how to transport simulation using dump data. Let's do exercise number 4. In this exercise, we will learn how to use dump data made in the exercise number 3 for transport simulation. To perform the transport simulation using the dump data, all you have to do is the 3 step described here. First one, please create the new source section with S type equals 17. Also, please set the old section to be, please set the old source section to be inactivated by using off, by writing the off. And second, please set cell ID number 102 to be void. Okay, void. Its material number is 0 because of the void. Third, please set T cross section, T cross tally with dump parameter to be inactivated by off. And note that the both two files, cross_hyphen _photon dump.out and cross_photon.out files are needed. When the dump ID 18 and 90 are included in the dump data, max gas and max batch of the first step written in the cross_photon.out are used, and max gas and max batch in the input file of the second step are ignored. Okay, from now I make some time, so please try this exercise in the same manner as the previous exercise. When you finish this exercise, please let me know using the reaction button yes. I think that most of the participants are still working, but I would like to do this exercise with all of you. So the answer is shown in the next page. So seeing the answer, I will do this exercise from now. So here is an answer of the exercise number 4. So to perform the transport simulation using the dump data, so all we have to do is first to create a new source section with S type equals 17. So I think better to copy the source section and modifying the S type value to be 17. And after that, writing down 5 equals cross underbar bottom underbar dump dot out and dump equals -11. And also I have to define the ID number of dump parameter 1, 2, 3, 4, 5, 6, 7, 8, 9, and 18 and 19. That's all. Okay. And also we have to set the old source section to be inactivated by off. And second one is to set cell number 102 to be void. So moving on to the cell section, and we have to change this value to be 0. And third one is to set the T cross section with a dump parameter here to be with the dump parameter to be inactivated. So just writing down off. So by using off. Okay, after the changing, so I will execute the bits, hoping the running without any error message. Okay. After the execution, everyone please open the track underbar exit.eps file. Okay, perfect. As shown in this figure, radiation particles included in the dump data are generated behind the water. Okay, let's do the final exercise number 5. In the exercise, from now, I will put a lead block behind the water and simulate the radiation shielding. To make the geometry and to perform the simulation, all we have to do is the 3 step described below. The first one, please change the material of the cell 102 to lead with isotope ratio. See the light table. And the density of lead is 11.34 gram per cubic centimeter. This means that you need to change some parameter in the material section and cell section. Second one, in order to study an effect of the sealing, please define a new cell ID number 103, a cylindrical region with 10 centimeter radius and 1 centimeter thickness. Third, in the second P-cross study, please add one condition to count the number of photons moving from cell 100 ID number 102 to 103. Set its area to be pi times 10 square in centimeter square. Okay, from now I make a couple of minutes. So please try this exercise, and after you finished this exercise, please let me know using the reaction yes. Please try. Everyone, sorry, it's time. So let me explain the answer of exercise number 5. Seeing the answer, so let's do the exercise with me. So moving on to the next slide. So here is an answer of exercise number 5. So to put a lead block behind the water, all we have to do is this. So first one is to add material number 2 and define the lead in the material section like this. So moving on to the material section, and copy and paste and define the new material number ID2 and defining the lead like this. And after that, second one is to change the Z coordinates of surface number 15. So adding the PZ and the value of 25, 20, 26. And is this correct? Okay. After that, third one is to modify the material number and the density of the cell ID number 102. So moving on to the cell section and focusing on the ID number 102, changing the material number, material ID, and defining the density of lead. And after modification, so newly adding the ID number 103 and write down 0, minus 11, 14, and minus 15. And of course, we have to write down, we have to remove the double defined region. So writing down sharp 103. And fourth, to add one condition to count the number of photons moving from the cell 102 to 103, and to set its area to be 5 times 10 square in centimeters square. So adding the new condition from 102 and 103. That's all. Okay, let's execute the fits. Oh. I see. Sorry, I forgot to modify the region number. So I have to change the region number from 2 to 3 because the number of the condition is 3. Okay. Then I will try it again. Good. Okay. After this execution, let's open the track underbar exit.eps file. This one. Then you can have this kind of the result and found that the particle fluence is recorded in the lead region. The particle fluence is reduced in the lead region. Okay. And please, in the same manner, please open the output file named cross underbar eng.eps file and go to the third page. Go to the third page. The left figure depicts the energy spectrum of photons coming into the lead region we initially obtained this lecture. The right figure is a spectrum after the lead shielding. From the right figure, the lead block should reduce the intensity of cobalt-60 gamma rays to approximately 1/10. Okay, in summary, we can perform a two-step simulation using dump data. A correct statistical process using the I-dump mode equal 1 can be applied by recording the dump ID 18 and 19. Before finishing this lecture, I have to tell you about the several notes of the dump data in the fixed code. So first, note about the idump mode equals 1. First, the thought fact is reflected the setting of thought fact in the first step at the time of making the dump data and the calculation of the second step using the dump data. The option idump mode equals 1 is incompatible with the merge source. In the second step, the negative ISTDEV value, research calculation mode, or dump all equals 1 in permitted section cannot be used. Okay? And max cast and max batch in the input file of the second step are ignored. And if you use all the statistical process of fits, please set idump mode equals 0. And with idump mode equals 1, the option that dump mode can control the number of reuse of the dump file. Second, note of the parallel computing. The OpenMP can be used in the first step calculation, while it cannot be used in the second step. And MPI can be used. Of course, the MPI can be used when the number of processor elements in the first and second step is the same. And finally, I would like to introduce the useful converters, MCPL converters for fits. As described in this slide, the dump data converter developed by Dr. Douglas is available. And the dump data in the fits, NCMP, or Giant4 format can be converted to those in the other code format. And this converter can be used as a command line in the terminal on Linux, Mac, Windows system. If you are interested in these converters, please see the URL described here. Okay, that's all. Thank you very much for your kind attention. It's time to finish. Ogawa-san, now that we have finished, so please make some announcements for the next optional lecture.
Thank you, Yusuke, for source B lecture, going through up to the very end. So as Yusuke mentioned just before, we are going to proceed to optional lectures after 10 minutes of break. Let me share the screen. So in 10 minutes, we will be either staying in the session or moving to other parallel sessions. You have choice of 3 optional lectures: accelerator and shielding design, BNCT, or X-ray therapy. Please select one of the optional lectures to take. And if you would like to take accelerator and shielding design session, please stay in this session. If you would like to take either BNCT or X-ray therapy sessions, please click breakout rooms and move to breakout room 2 to go to BNCT, and breakout room 3 to go to X-ray therapy. Again, BNCT will be in breakout session 2. X-ray therapy is in breakout session 3. If you would like to take either BNCT or X-ray therapy, please move to breakout sessions 2 or 3. And now, tutors, please move to breakout session 2 and 3 to to see if the participants are moving into breakout sessions. So again, we will be moving on to optional sessions. If you would like to take accelerator and shielding design session, please stay, as this tutorial is starting in 7 minutes. If you would like to take BNCT optional lecture, please move to a breakout session number 2, breakout room number 2. If you would like to take X-ray therapy, please move to breakout session number 3. If any problems, please write on the Zoom chat. And the way to move to breakout sessions is to click breakout room icon on your Zoom toolbar, breakout rooms. In a Zoom toolbar, you can find breakout rooms menu. Once you click breakout rooms menu, a window pops up, which looks like this one. And in this pop-up window, please click Join button of breakout room 2 or 3. Is everyone okay? Just in case, if you have completely no idea which one to take, I would suggest to take accelerator and shielding design session. Because BNCT and X-ray therapy, they are a bit specialized in medical physics. Roshan kindly sent me the pop-up window. So the pop-up window looks like this. And if you want to go to a breakout room number 3, please click Join of this pop-up window. And please click Join of room number 2 to join BNCT session. If you are in trouble in moving to other sessions, we can move you by force. Please let me know on Zoom chat if you have trouble in controlling breakout room assignment. Now it's time to move to breakout sessions. Please move to breakout session number 2, 3, or stay in the session. We are going to start the session in 3 minutes. The contents of breakout session 2 and 3 are also recorded. Please don't worry. If you want to take more than one sessions, you can go to one of the sessions and you can watch the recording of the others later. All parallel sessions are going to be recorded. In 2 minutes, we will be starting the tutorial. By then, please move to breakout sessions. We will be starting the session soon. This main session is for accelerator and shielding design session. If you would like to take either BNCT or X-ray therapy, please click breakout room button and move to breakout session 2 or 3. If everyone is fine, let's move on to the contents of accelerator and shielding design. All right. So now it's time to move on to the tutorial content. This session is give me a sec. In this session, we are going to practice accelerator shielding, very practical example. Please go to a folder, Lecture, Advanced Shielding. Just in case, I'm going to be the speaker in this breakout session, in this main session. Tatsu Ogawa, one of the FITS development members. To go on to the content of accelerator shielding design, the session of the content of the main session, please go to the folder, FITS Lecture Advanced Shielding. Please open the PowerPoint slideshow. Radiation shielding design. As you have pasted to Zoom chat, we are at FITS Lecture Advanced Shielding folder. We are here. So let's begin. Throughout this lecture, we are going to practice very practical shielding calculation. The final goal of this exercise is therefore performing radiation shielding calculation in very actual practical maze structure, which is very common as the entrance of accelerator or RI facilities. And we actually calculate the dose rate in different important points throughout the maze structure and compare it with analytical calculation, which is often used in practical occasions. In fact, we can consider streaming of gamma rays through maze, and we can, for example, calculate the neutron shielding and activation of air around the beam dump of proton accelerator because radiation leakage and activation followed by gamma emission from activated air are very important factors in radiation shielding. And throughout this example, as this is a global international tutorial, we couldn't fix one regulatory quantities, so we use Japanese regulations as an example. Of course, you can use the regulation values of your country by making use of everything learned in this lecture. This lecture is composed of two steps, briefly. First, calculation of gamma ray streaming in concrete maze, and a second half is dedicated to calculation of neutron shielding and air activation around the beam dump of a proton accelerator facility. Let's try gamma ray streaming at first. And by the way, in the same way as the other lectures, when you have questions, you can raise hand to ask for a breakout session, or you can write on Zoom chat to ask general questions. Please don't hesitate to ask for breakout sessions or asking a question on Zoom chat. The rule is pretty much the same. So, usually in radiation shielding calculation in actual facilities, radiation safety experts, engineers use simplified formula for calculating dose rate because Monte Carlo calculation takes a long time, in particular using a full-scale geometry of concrete, maze, ducts, everything. So the very first thing to do is to check the accuracy of simplified formula to calculate dose rate and compare it with a FITS calculation. The simplified formula is based on a formalization explained in the slide. What is often used is the German industrial standard DIN formula, which gives the dose rate at the exit of two bent duct with a 90-degree bent angle. Please see this concrete maze structure. This is an RI, suppose that this is an RI source facility in which you use iridium 192 here. And this iridium 192 source is located at this red point, and we are going to calculate the dose rate at this point, P0, P1, P2, and P3. P3 is the exit of the maze, so what matters the most is the dose rate at P3, the end of usually the controlled area. And according to DIN formula, D0, the dose rate at P0 is calculated by this formula. Going to the second point, P1, the dose rate at P1 is D1, which is D0 times this factor. This factor depends on the geometric length of this maze. And then D2, the dose rate at P2 is formulated in this way. And the same thing goes for dose rate at P3, which is calculated by this formula. And to perform this calculation, we have a pre-made data table to do this math. So please open analytical methods .xlsx our spreadsheet, entering the length of this maze, and then let's calculate the dose rate at 0.1234. So first, as a first exercise, please try this exercise to enter distances, dimensions in this spreadsheet, and let's and calculate D0 to D3. Please try. Just in case, once again, I tell you what to do now. So we are at page number 5, and you are supposed to input the distances L0, L1, L2, L3, W, and H in these cells of Excel spreadsheet to calculate doses from D0 to D3. I give you another 2 minutes. If you have difficulty in finding the length of L0, L1, W, H, etc., actually all data are written here. You can simply copy and paste these distances to Excel spreadsheet if you are in trouble. So now it's time to go on. What we do in this exercise is to input the lengths in the spreadsheet. For example, L0 is 0.8, L1 is 1.5, L2 is 3, L3 is 1.5, W is 1, H is 2. Eventually, we get doses at different points. And this is how simplified formula like this one works. And these values are in complete agreement with the results shown in the subsequent slide. And these are the limitations in Japan. You can use your the values of your country if you want. But speaking of the Japanese regulations, assuming that P3.3 is the boundary of the controlled area, the exit of the maze, given that this is the end of the controlled area, the evaluated dose at the point should be below 3-month effective dose limit of 1.3 millisieverts. So maximum time that the iridium source can be used within 3 months is 1.3 millisieverts per 1.03 microsieverts per hour, meaning that are 1,262 hours. So this is the maximum operational period for which you can use this iridium source to be being compliant with a radiation regulation, and not to bring exposure to uncontrolled area beyond those limits. And given the situation, assuming 3 months is 13 weeks, which is equal to 2,184 hours, this iridium source must be stored in storage box outside the facility for 922 hours, and not to give contribution to the dose outside the controlled area. So this is what we can conclude from this calculation and dose limit. In this way, we determine the operation scenarios and time and irradiation time allocation of RA facilities. Next thing to do is to check the accuracy of this estimation using fits. Now it's time for fits. We go through 3 steps. First, check the source, and then calculate effective dose rate with a t-track, and then we learn t-point tally which is a point tally, there are functions equivalent in MCNP, Refluta, and other Monte Carlo codes. It's one of the tally functions with which you can get a flux with a very high time efficiency. We will be going through these 3 steps to calculate the dose rate. And finally, we compare the calculated dose. Here are some important notes about the radiation shielding calculation. A dose evaluated in shielding design is not absorbed dose because nobody use absorbed dose for radiation safety purpose. Very often, we use ambient dose or effective dose for safety purpose. And reduction of computational time is very often the key issue in shielding design because actual facilities are millimeters or sometimes kilometer large. In such calculation, a CPU time tend to be long, like days, weeks, or sometimes months. So saving CPU time is one of the top priorities. So event generator, EGS mode are not necessary in most of the cases. We often turn off these functions for the sake of CPU time. And this is a note for practical application. Very often for shielding calculation, we do not 100% depend on FITs or simplified formula. We use both in a supplementary or complementary manner to supplement the other because simplified formula has lots of approximation, so they might be inaccurate, while FIT is accurate but very time consuming. So we need to combine these two to finally get reliable data in reasonable time frame. Please go to Maze folder in shielding folder. Please remember that we are at its lecture advanced shielding. And please move to Maze. In Maze folder, please open maze.inp. This is the starting point of maze.inp file. For the first step, let's run this input file without changing anything. You can visualize the geometry. By running this input file and opening xztrack.eps, you see the initial configuration of the geometry. It's nothing but the maze that we saw just before. And please remember that we have iridium source at this red point, and we are going to calculate the dose rates at P1, P2, and P3. The first point here is omitted because the dose rate is obvious. We are going to calculate the doses at P1, P2, and P3. So please try exercise number 1. It's an exercise to check this source configuration. To do that, please change eye control to be 5 and set sources to be iridium-192 with a activity 200 gigabecquerels. There's one thing I didn't explain enough in detail. A question from Stefan in meeting chat. In shielding calculation, we are not going to use EGS. It means that photons are transported not by EGS, but by Fitt's native algorithm, which is activated by an EGS equals -1. So Stefan's comment is correct. Actually, an EGS parameter is -1 by default. Actually, in parameter sections, section, there are no EGS, an EGS parameter because we are going to use an EGS -1, which is the default. And that is an option to use Fitt's native photon transport algorithm. If it's clear, please try exercise number 1. And when you finish, please turn on yes sign from reaction menu. Please try. All right. Just in case, if you are in trouble, let's do it together. Now it's time for the answer. This exercise, we change eye control from 8 to 5. Scrolling down in this file, the source definition is like this. And actually, iridium-192 200 gigabecquerel source is already defined in this way. E-type equals 28 means RI source definition, and I means to use 1 RI, and the RI is iridium-192 200 gigabecquerel, and normalization is per second. So everything must be fine. Let's run. In this way, we can get a flux distribution by replacing everything with a void. Like here, this must be concrete, but as I control is 5, so everything is replaced with a vacuum. The radiation from the source penetrates everything. And apparently, we see some particle fluxes in different points. As it is a follow-up, let me answer to the question in meeting chat. When should one use EGS instead of the original Fitts algorithm, and why is the original algorithm faster? There's one thing I didn't mention when I replied to one of the previous questions. Actually, well, in this calculation, an EGS is not defined using a -1. So we use Fitts native algorithm instead of EGS. And in this case, photons are transported and electrons are not transported. Fitts native algorithm cannot transport electrons. It's dedicated to photons. And that's exactly why Fitts native algorithm is faster. Basically, in electron photon transport, what takes CPU time is electron transport. Inversely speaking, well, when you would like to get accurate photon electron transport calculation data, you need EGS, and EGS equals 1, because EGS is much more precise than Fitts native algorithm, in particular when it comes to electron transport. And another question, is there any conversion factor between flux to dose rate? It's something you can activate by using a multiplier function. If I remember correctly, we will be using the multiplier to convert flux to dose rate, ambient dose rate and effective dose rate. We will be getting to this point very soon. Oh, exactly. That's in the next slide. So, as I mentioned just before, we don't use observed dose, physical dose, but instead we use conversion factor to get effective dose rate or ambient dose. To get those operational quantities, we use T-track, T-point, combined with a multiplier. And this is something we learned yesterday, that by defining a multiplier subsection in T-track or T-point, anyway, in tallies, you can convolute flux with those conversion coefficients to finally get doses in the unit of sieverts. And in this case, the conversion coefficient is a -202, which is for effective dose based on ICRP publication 103 AP irradiation. Of course, you can use other dose conversion coefficients. And to convert the dose rate to the unit that you want for operational, to meet with operational limitations, you need to convert the unit of time, such as per second to per hour, and convert picosieverts to microsieverts. So please be mindful about the units of time and sieverts. So let's go on to exercise number 2. Here, we are going to get the dose rate by using T-track tally. For that, please change eye control because as long as eye control is 5, everything is void. And please set max fetch to be 10. After changing these parameters, please run this input file and check XZ track EPS and those track.out. Go ahead. When you finish this exercise, please turn on yes sign in the reaction menu. All right, let's go on. If we are in trouble, please have a look at the screen. Let's do it together. In this exercise, exercise number 2, let's change eye control from 5 to 0. Max fetch 10. And everything else, like T-track, is already set. T-track starts at line number 97. Everything is set already. So let's run. This actually takes a bit long time because particles are actually transported. In my computer, it takes about 20 seconds. Despite this long CPU time, what we get is very poor statistics. Let's see. XZ track xztrack.out. This is the output of ttrack. No, it isn't. trackDose.out, sorry. So trackDose.out is the output of ttrack, which calculates the dose rates at P1, P2, and P3. The doses are like this, and that. And the problem here is that the uncertainty is terribly high. At the very end of the maze, where the dose rate is the most important, the uncertainty is 71%. I would say that this is not at all reliable. We cannot use this value for actual operation of facilities. That's why we then use T-point tally to get those in reasonable CPU time. It is impractical to calculate particle full length at a certain point using ttrack. What we were doing was to calculate the dose in P1, P2, and P3. As we can clearly see, the particles are very sparse at P3, and this is what caused this bad statistical accuracy. And as the nature of ttrack scores the particles which crossed this region. So this dose is the dose at P3 is attributed to the particles which actually crossed this cell. Unlike ttrack, T-point can be evaluated by calculating the directional and transmission probabilities to the tally position at the source location or at the point where the particle is generated by scattering. This means that every time when particle is either created or scattered, a T-point can get tally contributions. So it is a bit CPU heavy, but after all, this calculation method is very fast because T-point can count a contribution, can get contribution from particles at every scattering or particle generation. But one of the drawbacks of T-point is that it can tally only the angular and energy distribution of the produced particle at the scattering point alone in advance, which means that T-point can be used for neutrons and photons transported based on evaluated cross-sections. In other words, you cannot use T-point for proton irradiation, ion irradiation, because we do not have evaluated cross-section data for protons or ions. But in this example, the radiation source is gamma ray, so we can safely apply this T-point tally to calculate those. And here's the list of conditions in which you can safely use T-point. For more detail about the theory of T-point, you can go to FIT's utility T-point, as mentioned in Zoom chat also. Let's go on to exercise number 3, a calculation of effective dose rate with a T-point. In the input file, we have T-point starting at line number 163. So this exercise number 3, is to activate this tally and run fits again. So please try this exercise, and when finished, please raise your hand. Please turn on yes reaction. All right, let's move on. In exercise number 3, let's delete off after T-point. And all the details for T-point tally are already defined here. Here's the specification of the coordinates where we would like to know the dose rate, and a multiplier is applied to calculate effective dose. So just after deleting off of T-point, let's run. And then this time it takes a bit long because this input file runs not only T-track, but also a T-point. Calculation goes on. And at the end, you will get the results of a T-point tally, which should look like this. The dose at the first point is in the first section. The dose at the second point will be here. And the dose at the very end comes here. What is wonderful about T-point tally is the dose rate, statistical uncertainty is just 9%, even at the end. Please remember that the error of T-track was about 70%. Now it's just 9%. It's very small, meaning very accurate statistically. So let's move on to the next page. And here, please fill out this table to compare the calculated dose rates. We will be taking 10 minutes break. So before taking break, please quickly fill out this table and let's get conclusion. Let's get the conclusion of the first half of this exercise after the break. So let's have 10 minutes break. Thank you. Now it's time to resume. Hopefully, you have filled out the tables to summarize the result of calculations. And filling out the table, the result will be like that. DIN formula, the simplified formula, has given you these values, while Fitz T-track and T-point gave you these values with unit of microsieverts per hour. And here is the ratio of DIN divided by T-point. Probably these values might be slightly different owing to the version a random number sequence different between Fitz versions. Anyways, minor details doesn't really matter. What's important here is that the ratio of DIN and T-point is about a factor of 3. DIN gives the value about 3 times lower. But anyways, based on these dose rates, we can finally calculate the maximum usable time of this iridium source within 3 months. That is 1,262 hours based on DIN calculation and 448 hours based on Fitz T-point calculation. They agree more or less by a factor of 3. And concerning one of the questions on Zoom chat, what is the requested accuracy of these calculations? Fitz itself can be accurate up to some percent. If actually in this calculation, the uncertainty was about 10%. So we can achieve accuracy up to 10% in Fitz, but globally speaking, in wider view, there are some noticeable difference between these empirical formula and Monte Carlo calculation by Fitz, which is as large as about factor of 3. So usually a safety factor of about 3 or sometimes 10 is considered as a safety factor. So we have finished the first part, gamma ray streaming in concrete maze. Let's go on to the second part, calculation of neutron shielding and air activation around the beam dump of a proton accelerator facility. In the shielding design of proton accelerator facilities, a simplified formula is used to calculate the neutron dose behind the shielding in the same way as gamma facilities. Let's compare the result of dose rate from the simplified formula and Fitz. Again, we take a similar approach as gamma shielding. And in addition, what happens in neutron accelerator facilities in which neutron flux is not negligible, air activation matters. So in addition to the comparison of a prompt dose rate, we are going to calculate the activation of air around the beam dump, because around the beam dump, activation is the largest. In this example, for proton accelerator and the subsequent neutron neutron transport, to calculate dose rate by neutrons, we used a Tesh formula. And Tesh formula is formalized in this way, using a neutron dose equivalent beam loss rate, a dose equivalent attenuation length, a distance from source to evaluation point, and thickness of shielding material to take into account for the source configuration and the shielding. This time, we are going to calculate the dose where features have seats here, because this is the area accessible by engineers during operation. And here's the list of calculation conditions: 400 MeV, a 250 kilowatt proton beam, and this beam is stopped by copper target. The value of H cask for 400 MeV proton is 2.10 to minus 15 sieverts meter square per proton. This is a data taken from a pre-evaluated database. And this is also taken from pre-evaluated data, that is lambda, which is 90 gram per square centimeters. Thickness and density of concrete shield are 50 centimeter, this concrete shielding, 50 centimeter thick, and 2.2 gram per cubic centimeter. That's the assumptions. That's the assumption. And given these conditions, let's calculate the neutron dose rate in sieverts per second on the concrete shield at 90 degrees. So beam is this way, and the phaeton is at 90 degrees in respect to the beam axis. To calculate the dose rate using analytical formula, let's move on to let's move on to the same spreadsheet, but different page, a different sheet of the spreadsheet. In the second sheet, there's a sheet named TESH, and this is the pre-made table to calculate the dose in this condition using the parameters of this irradiation facility. So first of all, please try this exercise to fill out these 3 cells to calculate the dose. Please try. When finished, please turn on yes sign, yes reaction. 11 of you have finished. I give you 2 more minutes. All right, now it's time for answer. The distance between target and evaluation point is 1.5. Density of the shielding is 2.2. Thickness of the shielding is 50 centimeter. So this is the answer. That is 1 sievert per second, which is pretty high value. Could be dangerous for people. So by entering 1.5 meter as the distance between the target and the evaluation point, a 2.2 gram per cubic centimeter as the density of the shielding, and a 50 centimeter as the shielding thickness, we get the dose at the evaluation point. And in the same way as gamma shielding, we then switch to Fitts calculation to compare this value with the result of a Fitts calculation. This time we go through 7 steps. Please don't give up. Let's go on. First, let's check the geometry. Please go to accelerator folder and please open accelerator.inp. This is the input file to start with. By running this input file without changing anything, you might see some messages, but don't care about it. Anyway, geometry is plotted. And geometry is shown as EPS file. We see that there is a void, probably the beam line, and copper target is at the end of the beam line. And we see a concrete shielding and evaluation point. Let's go on. In this calculation, the source particle is 400 MeV protons. And Dmax1 and Dmax2 are set to be 200 in this input file, as we see at line number 9 and 10. These values, Dmax1 and Dmax2, means the maximum energy of the proton cross-section data library. 2 means cross-section data library upper limit energy for neutrons. And in this calculation, we use a Gendel 4.0 high energy cross-section data to obtain reliable shielding calculation results. Some details on this cross-section data library is provided in a paper, this one, in Journal of Nuclear Science and Technology. And by default, Fitts package contains Gendel 4 high energy cross-section for these limited nuclei. If you would like to use cross-section data libraries, actually this info is a bit old because Gendel 4.0 high energy is not the latest. They released Gendel 5. So to perform precise calculation, I would suggest to use Gendel 5. And Gendel 5 cross-section data library has data up to 200 MeV. And in this input file, you see warning messages like these ones. because, for example, 11023.51.51c means the cross-section data for sodium, which is not present in the default package. That's why FITS is nagging, saying these cross-section data are missing. Anyway, we don't have to care about it because what's important in shielding calculation are these elements. And this info is also a bit old because we do not use Gendel 4.0 high energy anymore. We use Gendel 5. So please don't care about this. Anyways, let's go on to an exercise. Normal particle transport simulation to get inside to have to grasp what is doing in this calculation. So please try exercise number 1. In which you change eye control and run this input file with this normalization. Please try. All right, let's do this exercise together if you haven't done yet. So please change eye control parameter to 0 to perform normal transport simulation. Probably in your computer too, fits would be lagging like that, but don't just forget them. Just keep going. And after running this input file, you get a result of the transport xz-track.eps. As in the same way as the previous gamma shielding, the particle flux at the evaluation point, cell 11, is very sparse. So it is very likely that the statistical uncertainty is terribly bad at cell 11. In fact, in my computer, the result is like this. Oh, it is true. There's a mistype of the file name. It's yz-track.eps, not xz. Thank you. And then let's go on to the next one. This can perform two-step calculation using information on particle coming into specified regions. This is exactly what we did in source B lecture. We dump the particles at a certain plane and use this dumped data in the subsequent transport step. So let's do this two-step calculation to accelerate calculation. As we learned in source B, we can dump various parameters of the particles, particle species, XYZ coordinates, XYZ components, directional cosines, energy, weight, time, counters, etc., etc. So exercise number 2 is to set outer void for dumped source. To record information on particle passing through the air as dump data, we must set the outer void behind the air, not to double count particles. So please follow these instructions to complete exercise number 2. Please try. All right, let's do this exercise together. In the input file, we are going to replace the concrete with the void. To do that, first, we change eye control parameter to visualize the geometry and scroll down to change the cell definition. cell 4 corresponding to this concrete layer is replaced with material number 1, and outer void does not have density, so density is void, empty. And if you run this input file, we again see the drawing of the geometry, which is like this. This white means outer void, so geometry is properly set. If everything is good, let's go on. If any trouble, please raise hand or ask in the Zoom chat. So please go on to exercise number 3. It's an exercise to create dumped source data. To do that, please enable two T-cross tallies. The first one is for dumping data, and the second one is to check the spectrum of the stored data. By that, we can perform a sanity check if particles are really dumped. And please don't forget to change eye control to 0 to perform particle transport. Please try. How is it going? Now it's time for answer. In this exercise number 3, please change eye control to 0 to perform particle transport simulation. And then please scroll down to T-cross tallies. First one is at line number 159, delete off, and going down again to go to line number 179. Please delete off again, and then run. This time, a calculation takes a bit longer because this calculation dumps particles to external file. This cross-neutron.dump.out is the dump file, which contains the tallied particle information. such as XYZ, velocity, angular cosine, energy, weight, etc. After this run, we get particles, and this cross eng.out is the histogram of particles dumped at this plane. As we replaced the concrete with a void, we see no particles here. Everything is dumped and stopped. Then exercise number 4 is an exercise to reduce the statistical uncertainty of dumped data. To do that, there's no golden way. Please change max CAS from 1000 to 5000. If it takes a bit too long, don't mind to use smaller values like 2000 or even 1500. Anyways, please run this input file with a larger max CAS to improve the statistics of dumped data. Please try exercise number 4. Let's increase max CAS and run. As there's nothing technically difficult, I do it here, 5000, and run. So in this exercise, what you do is to change max CAS to be something larger. It takes long as expected, but we can do nothing but wait until it finishes. So probably the CPU time very much depends on your computer performance. Please proceed up to exercise number 6. Now we are at 4. So please, when you finish exercise number 4, please proceed to exercise number 5 and up to 6. And I will be explaining in some minutes. So please go on up to exercise number 6. And please turn on yes reaction when you complete exercise number 6. Please go ahead. How is the progress? So after running exercise number 4, we can create relatively huge dump file cross neutron dump.out. As I used 5,000, the file size is 8.256 megabytes. And exercise number 5 is an exercise to make use of this dumped data. This time, we use the second source section here. And this is a source section to use dumped source, whose file name is cross-neutron dump.out. This is exactly what we have created in this folder. So we use this file as a source. This is the meaning of this source section. And this dump data specification must agree with the dump specification in here. Dump file was created by this T-cross, and this must agree with the data specification in source section. With this new configuration, we run this input. That is exercise number 5. Please go to exercise number 6. When you haven't finished, if you haven't finished exercise number 5, please continue. I give you some more minutes. Excuse me, in exercise number 5, I made a terrible mistake. It is true, creating new source section, activating new source section is important, and we have to set the concrete, the cell 4 to be concrete again. Please don't forget to revert this change to make cell number 4 concrete again. And also, it is no use dumping particles again. So please turn off E-cross with a dump, which is here at line number 159. Please turn off this T-cross, because this T-cross again tries to dump particles, which is not useful at all. Anyways, please complete exercise number 5 and exercise number 6. All right, let's go on. So after making use of the dumped data on the entrance of concrete shielding, we can perform simulation of the second step, that the neutron transport in this 50 centimeter thick concrete. And those detector.out should say something like 0.465 due to the different version difference and different random number sequence. It says 0.73 with anyway large uncertainty. So we finally got the dose, effective dose, but the statistical uncertainty is still high. And here, what we have to be careful is this second step calculation is based on the dumped data here. Usually, to improve the statistical accuracy, we increase max cast and max batch. But in this calculation, max batch and max cast cannot be increased. Technically, we can do it, but if we do that, this calculation might be skewed due to the overrepresentation of particles in dumped file. By using the dumped file twice, thrice, 4 times, 5 times, etc., then calculated result might be statistically skewed. To avoid such erroneous estimation of the dose, we use variance reduction technique. And this is exactly what we learned in variance reduction lectures yesterday and the day before yesterday. I do not get very much in detail again because we learned it already. So now it's time to use a weight window generator and make use of a weight window generator tally output as weight window setting. So please try exercise number 6 to get a better statistical accuracy. I give you 5 minutes. When you finish this exercise, please turn on yes reaction. All right, let's do this exercise together if you haven't finished yet. If you have done it, great job. Let's have a look. So the first thing to do in exercise number 6 is to activate TWWG to generate wait window section. And a TWWG can be found at line number 196. After deleting off, please run. And then this time we get wwg.out in the folder. In fact, wwg.out is created and updated at every batch. As we learned in Wait B lecture, the output of TWWG is formatted in the form of wait window section in this way. And here, the configurations of a wait window is given. So after running this input file with the TWWG, we go up at line number 11 to include the wait window, the result of wait window generator to this input file to perform iteration calculation, iteration of wait window generator and wait window. Then run. Again, we run this input file, but this time the particles are split to reduce the statistical uncertainty. By doing that, we can run iteration of wait window and wait window generator to help each other to accelerate calculation. Calculation goes on and on. I do not do it this time, but if you run this input file again, after this run, you can make calculation even more accurate thanks to the iteration. And you can run iterations 3 times, 4 times, etc., to make calculation more accurate. I do not do that this time. Instead, let's have a look at the tallied dose. This time, the statistical uncertainty is reduced down to 21%. If I run it again, it will be even smaller. So in this way, we can reduce the statistical uncertainty by making use of a wait window and wait window generator. Even though it is based on dumped data created on this surface, we can increase the statistics here. And based on this calculation, the dose rate is 0.7. Is it? In my computer, it's 0.56, but anyways, at 0.5 or 7 or something, sieverts per second. That is the result of its calculation. On the other hand, Tesh calculation, I told you that it's 1 sievert per second. So the ratio is about 1.4. Compared to the gamma shielding, in which the ratio was about 3, this is very good agreement. And what we can learn from this calculation is that 0.7 or 0.5 sievert per second is much higher than the dose limit, which is 2.6 microsieverts per hour. This is terribly high. So the lesson learned is 50 centimeter of concrete is totally inadequate, too thin. And Tesh formula says that the concrete has to be 800 centimeter thick. This is something we can calculate by Tesh formula and fits with the help of a larger dump file and more sophisticated variance reduction. Anyways, we need the support of analytical formula and fits calculation, making use of various techniques such as two-step calculation and variance reduction. Let's go on to the final part, air activation. So in this final exercise, we are going to calculate the dose by activation of air. In accelerator facilities, air is activated by spallation reactions, neutron capture reactions, etc. And these are dominant nuclei, in air are tritium, beryllium-7, carbon-11, nitrogen-13, oxygen-15, and argon-41. To calculate the dose by the air activation, we go through 2 steps. First, generate an input file for D chain and calculate neutron energy spectra and nucleide production from nuclear reactions using TD chain in FITS. This is what we learned yesterday in the lecture of D chain. And this is also one of the contents in D chain lecture. Calculate the radioactivity of nuclei during and after irradiation using D chain. So let's go on to exercise number 7. This time we switch to this folder, activation folder. So in this folder, please open activation.inp. And here, what we do, it's simple. Run fits with this input file, and run dchain with one of the output files of fits with air.out, which is input of dchain. So we run a 2-step calculation. Two-step calculation of fits and dchain. So please follow this guidance to perform this calculation. Go ahead. How is it going? Now it's time for answer. Activation.inp is mostly done already. Please scroll down to TD chain tally. All information necessary to calculate the activation of air is already defined. It assumes 1 day irradiation and 1 day cooling. And out time, the point of time when we observe the activation, are defined in this way. So please run this input file as it is. So in the first step, the proton beam is shot to the target with the kinetic energy of 400 MeV. And then neutrons, protons, and other secondary particles are created in the copper target. And such secondary particles like neutrons, protons, activates the nuclei in the air. After running FET's input file, activation.inp, please send air.out to dchain. Opening air.out, we run dchain either by shortcut command or from a GUI. Send to end dchain. Now it's done. One of the most interesting outputs is .act file, the summary of all produced nuclei. In this way, we can see the table of radioactive products due to neutrons and a direct reaction of high energy particles. The very first part is the data for 60 minutes from the beginning of history. And the second part is for 2 hours. We can get very details of activation in this file. And EPS file is very helpful to quickly grasp what the output says. For example, activity is more or less constant, rate is constant during a beam operation period, and it soon decays in the cooling period. Decay heat by beta, gamma, and alpha. And we can get the dose rate time evolution in this way. This might be probably something relevant to one of the questions we got in the lecture of dchain, are asking whether we can filter particular isotopes of interest. I if I remember right, I said no because I didn't remember this parameter. Angel out nuclides. By doing that, we can filter, we can pick up some isotopes of interest. As we are almost at the end of the session, I'm not going. Well, probably it might be nice to do it just in case. And in air.out, we can insert these lines after fits out, after a line saying fits out equals 1. After saving this dchain input file, we send air.out file to dchain again. Here we go. And then we get new outputs showing the contribution of the isotopes. I will be showing you once again. To do this, please get back to air.out file. And at line number 95 and 96, and just below fits out equals 1, please insert angel out nuclides equals 4 and specify for isotopes of interest. And after changing this this setup, send this file to dchain. Then you get updated EPS file. Yes, done. And you get new EPS file showing the contributions of isotopes of interest. Dose rate, decay heat, gamma heat, beta heat, and activity. In this way, we can filter contributions from a particular nuclide. So we are at the end of this long exercise. Throughout this exercise, we practiced a very practical shielding calculation. Dose evaluated in shielding design is usually either ambient dose or effective dose calculated by T-track or T-point with a multiplier function. This time we used our multiplier ID -202, which is effective dose. But depending on your calculation condition and the requirement given by the radiation regulation authority, please choose appropriate quantity to calculate. A two-step calculation using dump source and variance reduction methods are beneficial for reducing the CPU time, because CPU time really counts in practical shielding calculations. Activation calculation can be performed by combining fits and dechain. By that, you can calculate the activation of air. And in practice, the actual licensing application may consider facility-specific safety likelihood or safety factor. For example, factor of 2. Due to the systematic uncertainty of fit simulation. There are actually two uncertainties to be considered: the statistical uncertainty and the systematic uncertainty. Statistical uncertainty is what you get in fits output, and this is something you can reduce by making use of variance reduction, a two-step calculation, or large max cast or max batch. But the other uncertainty, systematic uncertainty, cannot be reduced as long as you are using one code. To reduce systematic uncertainty, you can, for example, benchmark fits or use other codes for cross comparison. And due to such systematic uncertainty, you need to take into account for certain safety factor, which is about factor of 2, 3, or sometimes factor of 10. I would suggest to make sure what is the safety factor of radiation regulation authority of your country if you use these approaches in your actual work. That's all for this exercise. Thank you very much. If you have any questions, please raise your hand so that tutors can take you to breakout sessions, or you can write questions in Zoom chat. We will be answering to your question. If no questions, please leave the session. And one thing, if you would like to discuss the CPU time, which depends on the type of CPUs, which is discussed in the link which I pasted. Please remain in the session, and please contact Takuya Furuta, one of the tutors. If you would like to discuss this subject, please stay in the session and contact Takuya Furuta. So, just in case, I will double check if there's nothing left for today. I think it's all done. So those who have questions, please raise hand or write in Zoom chat. And if no questions or no problems, please leave the session. Thank you very much. See you tomorrow. Bye-bye. Thank you very much. See you tomorrow. Thank you very much. Thank you very much. See you. See you tomorrow. Thank you very much. Have a nice day or have a nice evening. Thank you very much. See you tomorrow. Bye-bye.